right? Like we could talk about, especially like yesterday we did the polynomial, like third degree. We don't really know about the turning points, but this is a quadratic. Which way is this quadratic going to open? Which means I could tell you right now that there's going to be a minimum value. It's just finding that minimum value, right? So we've done this for years in terms of finding the vertex. Now we can use calculus to do this a little quicker. So we talked about yesterday, you check the endpoints. Well, the domain of this is all real numbers, so there's no endpoints to check. And then you find those critical points, the turning points in that graph. So to do that, I could take the derivative of this, which would be, oh man, this is a nice derivative, 4x minus 8. And to find the critical points, I just set that equal to 0, add 8, divide by 4, and I get x equals 2. Which should be the same thing you would get if you did the vertex of that, whether you did negative b over 2a or whether you did vertex form. You should still get that that is at 2. And since we know it's a quadratic, we don't have to check the graph because we already know that it's going to open up, and we could just plug that back in there to find the actual minimum value. So I could just say 2 times 4 minus 16 plus 9. I don't know why I wrote that, but then the rest. Negative 8 plus 9 is 1. So I could say there is a minimum at the point 2, 1. Did I do my math right? 21 is a third degree, and third degree you don't really know, is it a max or a min, a local max or a local min, which is where you can find the critical values to do that. Is it quicker to just do the vertex of that and find that point? Probably on a quadratic, but I just want to show you that the calculus does work to do that as well. Let's do some ugly ones today, since you didn't do the other ones anyway. I don't know that I printed your notes out because it's just 2 examples. I know. What am I thinking, right? But I don't think I printed them out because you would never fit them on the little box that I print out. That's the one problem. I can give you a blank sheet of paper if you need, but you need a piece of paper. Do you want lines or no lines?
Lines.
What have we come to in calculus class? Same directions as yesterday, just wanted to do kind of an uglier problem maybe. How do you want to take the derivative of this? You could do the product rule. You could distribute first if you want. You just have to deal with fractional exponents there. I did the product rule on mine. Nothing that says you have to do the product rule if you want to distribute. But yeah, let's just do the product rule. Good practice, right? So I'm doing the derivative because I'm looking for those critical points. So the derivative of x to the 2/3 would be 2/3 x to the negative 1/3 times x squared minus 4 plus leave x to the 2/3 alone, and the derivative of that would just be 2x. And we have to solve this, which means we have to get this simplified to a point that we can set it equal to 0 and that we can solve that without the calculator's assistance. You have some options here. One option is we could try to factor some stuff out. Another option is we could get a common denominator because, why do I say denominator? Because if I wrote this all together, do you agree that that's like 2 times x squared minus 4 all over 3 times x to the 1/3, or the cube root of x? Oh, how you want to write it? I'm going to write x to the 1/3. So whenever I see negative exponents, I always think 2 options. One option is write it as a fraction and get a common denominator. The other option is factor out the negative exponent, and you have to remember all your exponent rules that when you factor it out that you're subtracting. I don't know, it's kind of weird. But we'll just do this on this one. What's x to the 2/3 times 2x going to give me? What do I do with exponents when I multiply? I add them, so that would be like 3/3 plus 2/3. Would that give me 2x to the 5/3 right now? So doing the derivative is still important, but the algebra of it becomes really important as well, which is why you have to make sure you get caught up on that homework over the weekend if you haven't done it yet, so that you can have some practice of doing the algebra. Are you able to solve it and get those critical points? So if I want to get a common denominator, I just need to multiply this one by 3x to the 1/3, and it actually kind of works out really cool. Over here I have, I'm going to go ahead and distribute that. I'm going to say 2x squared minus 8 over my denominator, x to the 1/3. Bless you. Here I get plus 2 times 3 is 6. What do I get when I take x to the 5/3 times x to the 1/3? Yeah, because 5/3 plus 1/3 is 6/3, and so it works out to x squared when you're doing that. So if I set that equal to 0, 2x squared plus 6x squared is 8x squared minus 8 over 3x to the 1/3. Remember that critical points are where your derivative equals 0 or where your derivative is undefined. So you do have to think about that denominator at some point. But to solve the top part, right, you can just multiply that over and you just have 8x squared minus 8 equals 0. So if we add 8 and divide by 8, that would just be 1. We would get plus or minus 1. But also, I'm going to say, I always write it like this. X can't equal 0 in this because it would be undefined because x is in the bottom. That's also a critical point. As long as when I plug it back in over there that I can do it, and you can. You can take 0 to the 2/3 power, and you can plug 0 in there. So even though it's undefined in my derivative, it's a critical point for my problem. Does the extreme value theorem apply to this problem? No, because it's not a closed domain, which means to check these, we can plug them in, we can get the values, but right now, we're going to look at our calculator to determine which ones are max and which ones are min values. So now that I have my critical points, I'm just going to, I think I have it flipped. So I'm just going to take my values, x equals -1, x equals 0, and x equals 1, and I'm just going to plug them in to see the y values that I get. And eventually next week, we won't need to use our calculator at all, but then today we're going to look at our calculator to say which ones are relative or absolute max and mins. So without a calculator, could you do this? Could you say -1 to the 2/3 power times, that's just going to be 1 minus 4. -1 squared, cube root of 1, it's just 1, right? So is that just -3? And if I plug 0 in there, I think that's just going to be 0, right? 0 to the 2/3 power times anything is 0. And if I plug 1 in there, we get lots of weird exponents in calculus, and we plug 1 in a lot. And every year I have people that are like, what's 1 to the 5/2 power? What's 1 to this power? It's always 1. So we'll see how we get to that. But I think I also get -3. So I just want to caution you, don't assume that the biggest number is the max and the smallest number is min. It could work out like that, but just know it depends on what's happening at that part of the graph. Like -3 technically could be a relative max if that's a turning point on your graph at -3. Does that make sense? I don't know if that makes sense or not. But just you want to look at your graph, and eventually we'll do something called the first derivative test. You all have calculators today? Type this in your calculator, and you're really it's just nice practice to make sure you can type these fractional things in our calculator. And so, again, yours is going to look a little different than mine because you don't have the pretty print of when you do an exponent, you have to put parentheses there. You have to say parentheses 2 divided by 3 because yours doesn't automatically move it up like mine does, and I'm sure reference does. And then times, I don't know that you really need the times thing, but x squared minus 4. And I'm going to go to my window, and I'm just going to make my window -5 to 5. You could do zoom standard or zoom square, but I know I'm just looking at -1 and 1, so I'm not going to go very big. I don't know what, well, I do know my y value, so I'm just going to go like this. Oh, it's like a W. I'm going to use the calculator assistance. I had Teresa in there yesterday. Oh, I bet your y-axis, let's do this at your window. Your y is so far apart, it's not even looking at it. So change that to like -10 or something. I'm just going to do negative. Like you have your min-x and your max at it. Yeah, now hit graphics to maxes. There you go. Does it work now? And see again, like, here's, so just to kind of point out, we had an undefined derivative at x equals 0. Why was the derivative undefined at 0? What kind of point is that on my graph? It's a cusp. It still is a local maximum, but that's why it was an undefined point, because at a cusp or at a point, it could still have a local max or a local min, which is why you have to consider those in your critical points. So we can see that the, this actually has a minimum, not even a local minimum, right? So I would say there's a minimum at, I don't know how you want to write it, if you want to write the points, negative, we could even say this, we could be fancy, plus or minus 1, comma, -3. Is that the answer we have? Or you could say, just other ways that people say this, you could say a minimum of -3 at plus or minus 1, right? Because the minimum value is the y value, where it occurs is the x value. Either one of those is acceptable. And then we want to say a relative or a local maximum at 0, 0, or the same as saying a max of 0 occurs at 0 as well. But again, important that you use that word relative or local as needed. But the graph is what we needed to tell us this right now. So graphing calculators, definitely want to make sure you take those home to work on this homework. But I just want to encourage you to not use them until the end, right? Because if you graph it at first, you're like, well, I can just look and see where they are. But eventually I'm taking those away from you to do this. And so you just want to make sure that you're practicing the algebra of it, of getting those values, and then the graph to kind of confirm that. Questions about that? It really is just like an extension of what we did yesterday. And then the only other thing I want to do is talk about piecewise functions. So this is my last example. Same directions though. Find all extreme values. So piecewise functions, we talk about them all the time when we talk about limits and where derivatives exist. Piecewise functions make you have to think a little bit outside the box sometimes. So we can still do our critical points on this, we can still do all of that, but we might have to think about something else too as we start looking at what if we graph this. Are there any other points we need to think about on here? So before I graph this, let's just do if these were separate, I could do the derivative of each one, look at the critical points for each one, and think about what would happen there. So for the top part there, and I'm just going to write it as y equals 3 minus x. If I took the derivative of that, what do I get? Now let's think about that for a minute. That's a linear equation. Are you ever going to have a max or min or local max or min on a linear equation? No, it's a constant function, right? So that's never going to equal 0. So there's no critical points. And I'm okay if you get that and you don't have to show that work when you're doing homework problems or tests. But it should make sense that there's no critical points. On this one, if I did the derivative, again, kind of like number 19 that we went over, it's a quadratic, so we would get 2 minus 2x. We are going to get a critical point on that because as long as its turning point is in the part that we're graphing, we should get a max or a min on that. So again, just watch your signs there, but if I subtract 2 and divide by negative 2, I think I get 1. Did you hear that? It's not undefined anywhere, which means that's my only critical point. Before we graph this, can you tell me, is there any other thing I should be aware of that could possibly be a local max or min on this graph, or absolute max or min when you have a piecewise function? Like this point, you mean? Yeah, like where they meet up. Because think about when they meet up. They could meet up at a point or a cusp, or that might be a high point or low point on your graph. And so for piecewise functions, you might want to graph them, sketch the graph at least to kind of see what's happening. And if you haven't already graphed this, I saw you guys all making your graphs. Such good kids. We'll see there's an extra point on here that doesn't show up from the algebra, the calculus of it, that you have to check. So 3 minus x has a y-intercept of 3 and a slope of negative 1, so I have to go up 1, back 1. Okay. And on a test or a quiz, on the AP exam, if they don't give you a graph and you want to sketch the graph, it doesn't have to be perfect. You're just kind of looking to see what happens as you do this. Right? To graph this, I know that I can plug in 0 and see what I get. Right? I know the shape of it. So if I plug in 0 there, I'm going to get 3. Oh, look, they meet up. It's a pretty big circle. And if I plug 1 in there, I know from the calculus that 1 is the turning point. So that should be my vertex, and then I can go from down from there because it's opens down. But if I plug 1 in there, just do math correctly, 3 plus 2 is 5. 5 minus 1 is 4. And if you're aware that this point that we just found is the vertex, then you know that when you plug 2 in there, you should get the same thing, right? Like it should be turning back the other way. But if you didn't know, you can plug 2 in there, and you should get 3 again. Which means, I don't know why I made that point so big. I can kind of make that graph look like that. And so I just want to do this example to remind you that don't forget to check where they meet up to see if that is a extrema point on there. Because on this one, we could say that this point, which is the point 0, 3, and the point 1, 4 are both extreme values. What would 0, 3 be labeled as? A local minimum, right? Not an absolute minimum because this just keeps going down. And then if it wasn't for the piecewise function, that would be an absolute maximum. But because this side just keeps going up, we would have to say 1, 4 is just a local maximum or relative. I feel like I use them both just as frequently. I don't use one more than the other. Questions about that? Okay, so if you didn't do yesterday's homework, you have a lot of homework to do over the weekend because adding on to what we did yesterday, 35 through 45 odd, 48 and 49. And please, I encourage you to check your answers in the back piecewise functions on today's, and then a couple multiple choice questions too. And if you haven't ever paid attention on the multiple choice, if you find the directions on those, they always say whether or not you should be using a calculator, kind of practicing AP questions. So whether you pay attention or not, it's kind of worthwhile to look at, because sometimes it says you have to use a calculator to solve them, and sometimes, like on these, 48 and 49, it says you should be able to do these without a graphing calculator. So kind of something to think about. So if you need help